Hey everybody, I'm back, and today I'm going to look at the Unit 1 practice test solutions. That is the that is the first practice test we did, the one with the solutions that are posted outside my wall, so not the second practice test. All right, let's take a look at this. Okay, so which of the following 5 coordinate versus time graphs represent the motion of an object moving with a constant non-zero speed? Circle all that apply. Well, the speed, of course, is going to be indicated by the slope of the tangent line. So in something like that, the tangent line being the line that only touches the graph at one spot. So you see the slope here is going to be pretty shallow, and it's going to constantly increase, meaning the speed is getting greater and greater. In this case, the tangent line is the graph itself, because it is a linear graph. So in that case, the speed is going to be constant. So we have constant, and it's non-zero because the slope is rise over run, so it's going to be the negative change in x. I'm sorry, well, the change in x, which in this case is negative, over the change in t. The slope is 0, so the velocity is 0, because if you remember, average velocity equals change in x over change in t. Change in x here equals 0 over change in t. So average velocity equals 0 here. So that's out. In this case, you have a slope that's constantly changing, so you have a velocity that's constantly changing. So you will not have a constant velocity. It's a constantly changing velocity. And the same here, because the slope starts out 0 and becomes increasingly negative as time moves on. So this graph is the only graph that represents a constant non-zero speed. What is the relationship between instantaneous speed and instantaneous velocity? Well, instantaneous speed is the magnitude of the instantaneous velocity. That we just know by definition. They, of course, are not identical because speed and velocity are different. Instantaneous speed, blah, 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 blah. Well, no, this would be acceleration. That's out. They're unrelated. Well, of course, speed and velocity are related, so that's out. Average velocity is the initial speed minus the final speed. I'm sorry, I said that wrong. Average velocity is the initial position. Well, it's the final position minus the initial position over the change in time. Forget I said anything there. This option makes no sense, so it is obviously not the answer choice. Can an object have a positive acceleration and a decreasing speed? Well, if the object, well, yes. If the object has negative velocity, or the velocity is less than 0. Because if you're moving, let's say you're moving in this direction with some velocity and you're being accelerated in the other direction, all that means is your velocity is going to get smaller and smaller and smaller until the object turns around and then becomes faster and faster and faster, moves faster and faster and faster in the direction of the acceleration. So yes, this is possible if initial velocity is negative. This is not an option because if the initial velocity is 0 and is acted upon by a positive acceleration, its speed will increase in the direction of the accelerations. That's not correct. Yes, here this says yes, the speed will always decrease if the acceleration is positive. Well, no, not if velocity is greater than 0. If velocity is positive, speed will be increasing there. Yes, this is possible, but only if the object is moving in 2 dimensions. Well, not necessarily, because we described a one-dimensional example here that worked. Okay, so we're left with only one option. a stone thrown horizontally and it follows the path XYZ, the direction of the acceleration of the stone at point Y is, well, it's downward because it's downward everywhere. The acceleration in the X direction equals 0, as is always the case with projectile motion, and the acceleration in the Y direction is always negative 9.8 meters per second squared. So we would choose option A. What is 1 Newton in terms of fundamental SI units? Well, you've seen that about 400 times. The force equals mass times acceleration, so newtons equals kilograms times meters per second squared. Instruction sheet. Okay, we have one of these calculus problems here. The coordinate of an object is given as a function of time by this expression, this equation, where x is in meters and t is in seconds. Find the velocity at t equals 3 seconds. Okay, so you have the function x of t, I'll just rewrite that, equals 2t minus 3, minus t to the third. Well, in order to get the velocity, the instantaneous velocity, we must differentiate x with respect to t, or d dt of 2t minus, I did it again, minus t cubed equals, we can differentiate each term independently, and this is, I'll just say plus negative, d dt of negative t cubed. Well, we know that the derivative of this is 2 times, we're just going to pull that leading coefficient out, and we'll say 2 times the exponent, which is 1, times t to the exponent minus 1, 1 minus 1, plus the derivative of this, which is, we'll pull that negative 1 out, because that's the leading coefficient here. And we're going to multiply everything by the exponent of t, which is 3, and then we're going to throw back in t to the 3 minus 1. So if we simplify this a little bit, we have 2 times t to the 0th power, which is the same as 2 times 1, minus 3 t to the 3 minus 1, which is 2. So velocity equals 2 minus 3t squared. And so what is the time at t equals 3 seconds? Well, velocity at 3 seconds equals 2 minus, I'm just going to plug in 3 seconds here for t squared. So that's 2 minus 9, which is negative 7. And we know this is in meters per second because we're given the units up here. But you don't have to worry about the units too much during your calculation. So negative 3 meters per second. Okay. An object is thrown straight up from ground level with a speed of 50 meters per second. Find the distance above the ground 6 seconds later. I'm going to draw a little diagram. At some point, t equals 6 seconds, you're right here. Now, we don't even know which side of the trajectory it's going to be on. And again, the object is not moving laterally. I just kind of spread this out so you can see what's happening. It's going to come down P0. All right. Well, there's no motion in the x direction, so we can just say all the stuff equals 0. Just put an x through that. This is a one-dimensional kinematics problem. And we can define y0 as the 0 meter point. Y, and we want to find the distance above the ground level, so that we don't know, but that's the one we're looking for. We know what the initial velocity is. It's 50 meters per second. We don't know what this is. And of course we know what the acceleration is because it's the acceleration due to gravity, and time equals 6.0 seconds. So I'm probably going to start with my favorite equation. Y minus y0 equals v0y t plus 1/2 ay t squared. Let's see, we have everything we need. We have y0, that's going to be 0. We have the initial velocity in the y direction. We have the acceleration. We have time. So, and it's already algebraically formed for us with the unknown variable isolated and on the left side of the equation. So this is just a matter of plugging in numbers. Plus 1/2 times negative 9.8 meters per second squared times 6.0 squared. Again, I forgot to bring my calculator with me, and I don't want to stop recording, but you can churn that out and get a number. Okay. All right, find the angle between this vector and the positive x-axis. Well, you know this unit vector notation is, well, it's just a very convenient way of saying A equals AXI hat plus AY J hat. So this vector is already broken down into components for us, and I'm going to draw it out here. So it's going to be somewhere, oh, it's going to be pretty steep angle. This is your A vector, and the two components are AX and AY. And I can go ahead and label this theta. And I can transpose my AY over there if you wish. It's the same thing. And so we just have a right triangle. And if you remember right triangles, this question asks for the angle between the vector and the positive x-axis, so that is theta. Tangent of theta, and let's call this phi, so we don't mix it up with the theta over here, because I'm just talking in general terms over here. Tangent of phi is going to equal to opposite over adjacent. Remember Sakatoa? Tangent is opposite over adjacent. All this means is tangent of this angle, which is a unitless quantity, is equal to the ratio of the length of this opposite leg to the length of the adjacent leg. So this is a unitless ratio. And if you wanted to find the alpha phi, you would have to do the inverse tangent to each side. Okay, and the tangent and the inverse tangent cancel out. B over A. Okay, well, we've been just talking in the general sense here. Let's go back to our problem here. So in this case, tangent of theta is equal to the opposite to theta, the side of the triangle on the other side, opposite to the angle, over the adjacent leg of the triangle. And I can take the tangent inverse of each side. Tangents cancel out. Theta equals inverse tangent AY over AX. And now we can plug in some numbers. AY is 45 meters and AX is 25 meters. How did I know that? I know that just because this 45 meters is attached to j hat. So that means it is in the y direction. So it is AY. And the 25 meters here is attached to I hat, which means it's attached to the x direction. It is along the x direction. And that's all I hat and j hat mean. They just tell you the direction. It's just a convenient way to write these things. Again, I don't have my calculator handy, so I'll let you calculate that answer out. Okay, you are given two vectors. Find the difference a minus 2b and represent your answer in unit vector notation. Well, this is just some simple algebra. A equals ax I hat plus ay j hat. And b, these are vectors, equals bx I hat plus by j hat. So a minus 2b is going to equal ax minus 2bx I hat plus ay minus 2by j hat. All this is illustrating is that when you subtract vectors or you multiply vectors by a scalar, you manipulate them in any way, you're just treating the x and y components or the I hat and the j hat components separately. So you do the exact same thing to both sets of components. Well, we know from up here the AX portion of this is 2 meters minus 2 times the BX, which is 1 meter, and that's all I hat, plus a Y, which is negative 3 meters, don't forget the negative sign there, minus 2 times B y, which is negative 2 meters. And that's j hat. Again, because you're subtracting this vector, you have to add a negative, and then you have to keep the negative that was already there. So you're going to have a negative times a negative. So if we simplify this, 2 meters minus 2 meters, that's 0 I hat plus, well, I'll expand this out further. Negative 3 meters, negative 2 times negative 2 is plus 4 meters j hat. So A minus 2B is just 1 meter j hat. That's your answer. So the two x components completely canceled out once you performed this operation. So there are no x components left in the resultant. Okay, so we have a two-dimensional kinematics equation here. The diagram is already drawn for you, y0 and y. So I'm going to call y0 equal to 0, and y is equal to, I don't know, we need to find that. The dart is thrown horizontally at a speed of 20 meters per second, as shown. That automatically means that the final velocity in the x direction is 20 meters per second, because acceleration in the x direction equals 0. So that velocity in the x direction remains the same throughout the entire time of flight. We also read from the prompt here that t equals 0.1 seconds. And of course that's the same in each dimension. x0, we're going to say that starts at 0, just because we can do that, so why not define our origin as the starting point, or our 0 point as the starting point of the equation, the problem, excuse me. We don't know what that distance is. We don't know. So, well, let's go. We can fill in the velocity in the y direction too as 0 in the beginning because there's nothing here, and then it increases as the object continues to travel. The acceleration is negative 9.8 meters per second squared because it always is for an object in free fall. So what are we going to do? Well, I would think that we don't have the velocity in the y direction, so we can't use this equation. So we don't have that final velocity, so we can't use that. I would probably from y to y. What about another equation? What about y minus y0 equals v0yt plus 1/2 ayt squared? We have time. This is what we're after. We have the initial velocity. We can do it. So the initial velocity in the y direction is 0. y0 is 0. So y equals 1/2 ayt squared. And now I can just plug that stuff in. Y is 1/2 negative 9.8 meters per second squared times t, which is 0.1 seconds. So I guess just doing this off my head, this would be negative 4.9 times 0.1, so that'd be negative 0.49 meters. Wait, squared. So 0.1 times 0.1 would be 0.01. So that would be 0.049 meters. Check that solution. I don't have the calculator with me. But that is correct. You can check my numbers. Okay. A 25 kilogram crate is pushed across a frictionless floor with a force of 200 newtons directed 20 degrees below the horizontal. Find the magnitude of the normal force of the floor on the crate. Well, as always with these problems, I tell you, just don't try to guess your way to the end. Follow the protocol. So I'm going to draw a diagram. I'm going to come in with this force FA. 20 degrees below the horizontal, and we have FG, we have the normal force. So let's write down what we know. FA equals 200 newtons, theta equals 20 degrees, FG equals, mass equals 25 kilograms. All right, now I'm going to draw a free body diagram, because those are especially important. Well, let me give myself a little more room. I'm actually going to draw it down here. That'll make a little more sense. We know this is angle theta. Be very careful where you label your angles. That's the hardest part about this stuff. I see so many people making mistakes by labeling theta in the wrong position. So remember, this is 20 degrees below the horizontal, so all I'm doing is shifting this down to the center of the object. So again, this is theta is 20 degrees below the horizontal. If I wanted to break it down further, FG. Now I have to break this down into its parallel and perpendicular components. So this is just remember that the overall force is always the hypotenuse, and you're breaking that down into perpendicular and parallel components. So this is F-A-Y and F-A-X. And sine of theta is opposite F-A-Y over a hypotenuse, which is just F-A, and you have F-A. So now multiply each side by F-A. I guess I can squeeze it in here. That cancels. So F-A-Y equals F-A sine of theta. And likewise, cosine of theta equals the adjacent leg of the right triangle, F-A-X, over the hypotenuse, F-A. Multiply each side by F-A, and F-A-X equals F-A cosine of theta. So I can draw these forces up here. This is F-A-X, which is F-A cosine theta. And we have this other force here, which is F-A-Y equals F-A sine of theta. I don't know that this is actually smaller than the normal force was previously, but I'm sorry. Oops. That didn't make any sense whatsoever. This is F-A-Y equals F-A sine of theta. That made no sense whatsoever because these two components must add up to this vector right here. Sorry, please forgive me. And this is Fn. Okay, I didn't draw this vector smaller for any purpose other than to be able to see it. It could in fact be larger than Fg in magnitude. So let me list my forces. In the x direction, all I have is Fax. And the sum of the forces in the x direction is equal to mass times the acceleration in the x direction. We don't know what that equals because the prompt doesn't tell us if it is being pushed at a constant velocity or if it is being or if it's being accelerated. You can deduce from the situation that it says there's no friction and it doesn't mention any other forces working in the opposite direction. So if this is the only force acting on the object, then it cannot equal 0. Because that's the only force acting upon it. But the fact of the matter is all we're worried about with this problem is the normal force. So we're going to spend most of our time in the y dimension. So going back here and summing up our forces, I have the normal force and I have these two forces working in the opposite direction, Fg and Fay. And this equals mass times acceleration in the y direction, which does in fact have to equal 0 because the object, the crate here, is not floating or sinking. All the forces sum to 0. So let us do that. Sum of the forces in the f direction just equal Fa cosine of theta equals Max. And the sum of the forces in the y direction equal the normal force minus Fg minus Fa sine of theta equals 0. And of course the normal force now, I'm solving, I'm just adding, well, I'll go ahead and do it. Add Fg to each side. So now if I add Fa sine of theta to each side, oops, not equals. Okay? I can break down Fg a little more because we are not given the weight, we are given the mass. So this equals mg plus Fa sine of theta. And now you can just plug in. Equals mass, which is 25 kilograms times 9.8 meters per second squared, plus 200 newtons times sine of 20 degrees. Again, I'll let you plug those numbers in. Okay. All right, you got the muscle builder problem. With the guy holding the ends of the massless rope, the center of the rope, a 7.9 kilogram ball is hung as shown was the tension in one segment of the rope. And we're given the angle theta. I'm going to call this T1 and this T2. Okay, and I'm going to write down everything we know. Mass equals 7.9 kilograms. Theta equals 6.0 degrees. And that's all they tell us right now. Okay, so we have the schematic already done for us. And you're probably going to see we're going to break these vectors into components. And these two components are going to add and cancel each other out. But let's go ahead and draw a free body diagram down here. And again, you know, I have no idea where this problem is going. I really don't have any direction that I'm following right now. All I'm doing is breaking down all my forces and summing up all the components. So I'm just kind of following the protocol here. We have a force in this direction, T1, T2. We also have gravity, don't forget gravity, Fg. Now what are the angles? Well, this is theta. Okay, so well we can just work with that. I'm actually going to move the tension labels so I can fit theta in there. Now you could calculate this other angle here if you want to use that, but no, why bother? All right, so I'm going to draw another free body diagram. Gravity working downward. This is T2x, T1x, and you're going to have T2y and T1y. Again, these are along the same path in the y direction. I just drew them kind of separated like that so you can see them, you know, expanded. So what are these things equal to? Well, we have, let's draw our triangles again. T2, theta, T2x, T2y. Remember, the overall force, the big force at an angle, is always going to be the hypotenuse, and then we're breaking down into horizontal, perpendicular, and parallel components. So these two components are going to add together to get this hypotenuse. And we know that sine of theta equals the opposite leg to that angle, which is T2y, over the hypotenuse, which is T2. So T2y equals T2 sine of theta. Continuing on, cosine of theta is equal to the adjacent to that angle, T2y, over the hypotenuse, T2. So T2, did I say T2y? I meant T2x. T2x equals T2 cosine of theta. So I can put that up here. T2 cosine theta. T2y equals T2 sine of theta. Okay? Now, if I were to really do this rigorously again, we have T1, T1y, and T1x. So sine of theta equals the opposite T1y over the hypotenuse T1. So T1y equals T1 sine of theta. Cosine theta equals the adjacent to the angle T1x over hypotenuse T1. T1x equals T1 cosine of theta. So I can put T1 cosine of theta equals, and that equals T, excuse me, this was sine. And here is T1 cosine of theta. So let's sum up all these forces. In the x direction, I have T2x and negative T1x. T2 cosine of theta, negative T1x, which equals negative T1 cosine of theta. And these all sum to max, and we know that equals 0 because there's no motion. Everything is static. All right, well, in the y direction, we have T2 sine of theta and T1 sine of theta, and we have negative FG. And we know they sum to MAY, and that must equal 0 because it's static. So I know my page is getting kind of crowded here. I'm going to try to separate things out. Sum up the forces in the x direction. It's T2 cosine theta minus T1 cosine theta, and we said that equaled 0. So T2 cosine theta equals T1 cosine theta. Cosine theta is on each side, so if we divide each side by cosine of theta, that cancels out, and so does that. So we see T2 equals T1. Okay, that was obvious. You knew that from the beginning, but I wanted to prove that to you explicitly because what if one of these angles was not theta? What if we said one angle was a little different? Well, then you would have to come here and find out what they are. But we've proven for the same angle here, the two tensions are the same. So let's look in the y direction. T1 sine of theta plus T2 sine of theta minus FG equals 0. Well, we know now that T1 equals T2, so we can plug that in and say T1 sine of theta plus T1 sine of theta minus FG equals 0. Or 2T1 sine of theta, I'm going to move add FG to each side of the equation. So this equals FG. And I can divide each side by 2 sine of theta. And then T1 equals FG over 2 sine of theta, because these cancel out. Or, excuse me, mg, I'm just expanding FG to mg over 2 sine of theta, because we are given mass, not weight. You can plug those numbers in the calculator if you wish. All right, unfortunately, I have to go at this point, so I'm going to stop there, and I'll come back with another video finishing off this practice test.